Hello, this is my Level 3 Aerospace Engineering Project Prototype for a crosswind landing ratcheted mechanism in the landing gear of an aircraft to help with crosswind landings, to make them hopefully a little less dangerous and feel a little more safer for the passengers of commercial aircraft. Now what we have here is the full prototype, but to start off with I should mention the wheels, while they move and the suspension does work, it doesn't serve any purpose on this model. It is purely for aesthetics and to show you where the main system would be located. This stretched out section here is the main section. This is what we're going to be focusing on today. Now, as you can see, there's a big 40-tooth gear in the middle here and two 24-tooth gears along the sides. This 40-tooth gear is going to be what's connected to the main system landing gear and the aircraft body as a whole. So right now in this configuration, with the two gears acting as like pulls for the main ratchet system gear, as you can see, you can try and turn this middle section. It will wobble a bit because it's made out of Lego, but it cannot move. It cannot pivot. But when I color coded these beams here, down here in bright orange, so they'd be eye-catching, so you can see them better. When pressure is applied to one of these sides, you'll see that one of the gears will dislocate from the system. Now this allows us to move this whole 40-tooth gear system connected to the aircraft. You see, it cannot move clockwise because it's being stopped by this gear. Because from this gear being pushed outwards, this has pushed it in towards the gear more, towards the 40-tooth gear, sorry. So we cannot turn it anti-clockwise, but we can turn it clockwise, and it will kind of like ratchet. So I can turn it clockwise, but I cannot turn it back anti-clockwise. I can go on a full 360 degrees, no problems there. And when we release pressure on this, it will go back to the locked phase, or locked, phase, which means we cannot turn this at all. The same thing happens on this side. You apply pressure, gear gets dislocated, and now I cannot turn this one clockwise, but I can turn it anti-clockwise for as much as I please. Now, to show you how this system works, I just came up with this basically demonstration system. This doesn't work. It's not to scale. It's purely just to show you how this is working. So this lime beam here represents the straight beam, and this grey one is the V-shaped beam. These pins, the tan pins, to show you where the 24-tooth gears sit, and the blue one shows you where the 40-tooth gear sits. Now when pressure is applied to one of the sides, as you can see, it goes down like that. This one is the one that's dislocated from the circuit, and this one up here is the one that gets pushed in further to the circuit. So if I show you again on the main model, as I apply pressure to the left gets dislocated and the right gets pushed right in there. Fits real nicely in the tooth gears. Oh, don't roll away on me. Okay, so yeah, that's basically how this works. There are elastic bands on the bottom of each 24-tooth gears to like provide an equilibrium in the middle. So it's not going to shift from one side to the other. It'll always snap back right to the middle. I'll show you those now. This elastic band system is kind of messy because they do have to cross over each other, because this prototype isn't big enough for the elastic bands themselves just to retain enough tension. But if this was being made into an actual model, they wouldn't include elastic bands. It would be hydraulic springs, and you wouldn't have to apply pressure manually. it would be easier. Oh, there's also the elastic bands are attached to these. Sorry, these what do you call them? These pieces here, which are again attached to guide rods, which just allow the V-beam to pivot real nicely and kind of push the edge of the V-beam up against the straight beam here. And again, that allows everything to snap back quite nicely. And I believe that's pretty much it. Thank you for watching.